The night of March 23, 1945 settles cold over the Rhine River. German artillery thunders from the eastern bank. Shells scream through darkness, detonating in white bursts across the water. On the western shore, American engineers crouch in the mud, waiting for the barrage to lift. They carry pneumatic floats, steel treadways, anchor cables thick as a man's wrist. Their uniforms are soaked. Their hands shake, not from fear alone, but from exhaustion and the bone-deep cold of river water. Behind them, columns of Sherman tanks idle in blackout silence, engines rumbling low, waiting for a bridge that does not yet exist. German commanders watch from concrete bunkers 3 kilometers east. They have blown every crossing for 50 kilometers. They have mined the approaches. They have sighted their guns on every meter of shoreline. They know what rivers mean in war. They know how long bridges take to build, days, weeks. If the enemy is foolish enough to try under fire, by dawn, they will be proven catastrophically wrong. The engineers move forward into the darkness. Rivers had defined warfare in Europe for centuries. The Rhine, the Meuse, the Moselle, the Roer. These were not mere geographical features. They were barriers, moats carved by nature itself, wide enough to halt armies, deep enough to drown tanks. Medieval castles rose along their banks for a reason. Napoleonic campaigns pivoted on bridge seizures. In 1940, German forces had stormed across the Meuse at Sedan not through brute force alone, but through daring engineering. Pontoon, bridges thrown across under fire while Stuka dive bombers shattered French defensive positions. The Wehrmacht understood rivers intimately. Their doctrine treated every major waterway as a defensive line to be held at all costs. German military engineers, the Pionier, were among the finest in the world. They had built bridges across Polish rivers in days during the 1939 Blitzkrieg. They had spanned the Dnieper in the Soviet Union under conditions that broke lesser armies. Their equipment was robust, their training rigorous, their techniques proven across 2 world wars. When Germany turned to defense after 1943, rivers became fortresses. Every bridge was wired with demolitions. Approach roads were pre-sighted for artillery. Machine gun nests overlooked crossing points from reinforced positions. The philosophy was simple: force the enemy to stop, to build, to expose himself. A river crossing attempted under fire was a slaughter waiting to happen. History had proven this again and again, at Gallipoli, at the Somme, at 1,000 forgotten fords where men drowned in their own blood. The Allied invasion of Europe in June 1944 brought this reality into sharp focus. Normandy's hedgerows had slowed the advance, but rivers stopped it cold. The Seine, crossed in late August, cost days of preparation. The Moselle crossing in September consumed weeks of planning, stockpiling bridging equipment, coordinating air cover and artillery suppression. Each river was an operational pause, a chance for German forces to regroup, to dig in deeper, to prepare the next defensive line. By autumn 1944, the mathematics of river warfare seemed immutable. A defended river could delay an attacking force for days, sometimes weeks. Bridging operations required extensive preparation. Reconnaissance of banks and currents, assembly of equipment, suppression of enemy fire, construction under engineers exposed on open water. Even with air superiority, even with overwhelming artillery, the process was slow, methodical, predictable. German commanders planned their withdrawals accordingly. As Allied forces pushed through France and into Belgium, Wehrmacht units fell back in stages, blowing bridges behind them, establishing new defensive lines along the next river. Intelligence reports confirmed what German staff officers believed. American and British engineers were competent but conventional. They followed doctrine. They took time. A typical Bailey Bridge, the modular steel structure favored by Allied engineers, required 12 to 24 hours to construct under ideal conditions. Under fire, that timeline doubled or tripled. The Wehrmacht had weeks of warning before each river line fell, or so they calculated. But something was changing in the American engineer battalions pushing east through Europe. Something the Germans had not anticipated, could not have predicted from their intelligence assessments and prisoner interrogations. The U.S. Army Corps of Engineers had spent 2 years refining techniques, training men, stockpiling equipment designed for one purpose: speed, not merely competence. Not just adequate bridging, speed as a weapon itself. The doctrine was radical in its simplicity. Build faster than the enemy can react. Cross rivers before defensive positions solidify. Turn barriers into mere pauses, pauses into non-events. Keep armor moving, keep infantry pushing. Never allow the front to freeze into static warfare. The engineers would not wait for perfect conditions. They would build under fire, in darkness, in rain, in snow. They would build so fast it seemed impossible, and they had the tools to do it. The U.S. Army Engineer School at Fort Belvoir, Virginia, had been training men for this moment since 1942. Classes ran day and night. Engineer battalions practiced pontoon bridge assembly until they could perform it blindfolded, until every man knew every bolt and cable by touch alone. They trained in rivers, in lakes, in flooded quarries. They trained under simulated artillery fire with live ammunition cracking overhead. They trained in winter cold that froze their hands to metal. The instructors were merciless. A bridge that took 6 hours to build was unacceptable. 4 hours earned a nod. 2 hours was the goal. Some units achieved it in 90 minutes. The equipment reflected this obsession with speed. The M2 treadway bridge could be assembled from prefabricated sections, steel spans that locked together, pneumatic floats that inflated in minutes, anchor systems that required no complex engineering calculations. A single engineer company carried enough equipment to span a 200-meter river. The Bailey Bridge, borrowed from British design, used modular panels that bolted together without riveting or welding. No specialized tools required. No cranes needed. Just men, muscle, and method, but equipment alone explained nothing. The Soviet Union had pontoon bridges. Germany had excellent bridging systems. What made American engineer units different was not the hardware. It was the integration of speed into every aspect of doctrine. Reconnaissance teams crossed with infantry in the initial assault, surveying banks and currents while fighting still raged. Bridge components moved forward on trucks that stayed within kilometers of the front line, ready to deploy the instant a river was reached. Engineer battalions trained alongside the armored divisions they would support, learning to anticipate movement, to position equipment before orders. Arrived logistics became an art form. A typical engineer combat battalion consisted of 600 men organized into companies specializing in different tasks, one for reconnaissance and demolitions, one for bridge construction, one for road repair and maintenance. Behind them came bridge companies from the engineer group level, equipped with heavier pontoon systems capable of supporting 50-ton tanks. Further back, engineer depots stockpiled thousands of tons of bridging equipment, organized for rapid transportation to wherever the front demanded. The system worked because every level trusted the level below it. Company commanders knew their platoon leaders could execute without constant supervision. Platoon leaders knew their sergeants had drilled the men until bridge assembly was muscle memory. Sergeants knew their privates would work through exhaustion, through fear, through conditions that paralyzed thought. This was not blind obedience, it was confidence built through repetition, through shared suffering and training, through the knowledge that speed saved lives, because engineers who worked slowly died. German artillery and mortar fire prioritized bridge construction sites. Snipers targeted officers and NCOs directing operations. Luftwaffe fighter bombers, though increasingly rare by 1945, still struck at river crossings when they could penetrate Allied air cover. Engineers worked exposed on open water, visible for kilometers, unable to take cover while holding bridge sections or operating winches. Every minute on the river was a minute under potential fire. Speed was survival. The German expectation remained rooted in pre-war thinking. Their intelligence officers knew American industry produced vast quantities of equipment. They knew U.S. forces had excellent logistics, but they assumed, as any reasonable military mind would assume, that complexity required time. A pontoon bridge was an intricate construction. Currents had to be measured, anchors precisely positioned, spans carefully aligned. This was engineering, not magic. It demanded hours of methodical work. The Americans did not disagree with the physics. They simply trained until they could perform in 2 hours what should have taken 8. They simplified procedures, eliminated unnecessary steps, parallelized tasks so multiple crews worked simultaneously instead of sequentially. They rehearsed until a bridge construction site looked less like an engineering project and more like a factory floor. each man moving to his position, performing his task, moving to the next, the entire operation flowing like a machine. By late 1944, forward German commanders were filing reports that seemed impossible. Bridges appearing overnight. Rivers crossed within hours of American forces reaching the western bank. Armored columns rolling across pontoon spans before German artillery could range properly. The reports were dismissed as exaggeration, as panic from exhausted troops facing overwhelming Allied strength. Staff officers and warm headquarters refused to believe American engineers could work that quickly. The math simply didn't support it, but the math was wrong, because it calculated time based on conventional methods, conventional training, conventional urgency. It did not account for men who had been drilled until bridge building became instinct. It did not account for equipment designed from the first blueprint for rapid deployment. It did not account for a military culture that treated speed as a force multiplier equal to firepower or armor. The Rhine crossings would prove this beyond any doubt. Germany's greatest river, 400 meters wide in places, protected by the Wehrmacht's most experienced troops, defended with every weapon remaining in the German arsenal. The ultimate test of American engineering speed against German defensive doctrine. The engineers moved their equipment forward through the winter of 1945, stockpiling pontoons and treadways in forward depots, rehearsing procedures one final time. They knew what waited across the Rhine, the heart of Germany. The final collapse of the Third Reich. But first, they had to build a bridge where none existed, faster than the enemy believed possible. Angle 1. The human element, courage under fire. The engineers who built bridges were not combat infantry, but they died like them. Private First Class James Delmont of the 291st Engineer Combat Battalion wrote home in February 1945, "We don't carry rifles much. We carry cables and timbers. When the shooting starts, we keep working." This was not bravado. It was description. Engineers had personal weapons, M1 carbines, pistols, but their hands were occupied with bridge sections, winch handles, anchor cables. They could not return fire while guiding a pneumatic float into position against a 3-knot current. They could not take cover while bolting treadway spans together. They worked or the bridge did not get built. German machine gun fire raked bridge sites as standard procedure. Mortar teams bracketed the water with ranging shots, then poured high explosive rounds onto the engineers. Snipers, positioned in church steeples or ruined buildings, picked off NCOs shouting orders. The engineers learned to work in silence when possible, using hand signals, relying on rehearsed procedures that required no verbal communication. Still, men fell. Corporal Michael Russo drowned in the Moselle River in November 1944 when a pneumatic float ruptured under his feet. He was 22. Sergeant Thomas Chen took shrapnel through the chest while securing anchor cables on the Roer River in February 1945. He died before medics could reach him. The casualty rates for engineer battalions during river crossings sometimes exceeded those of assault infantry. Because infantry could go to ground, could find cover, could suppress enemy fire. Engineers had to stand in the open water and build, yet they kept building, company after company, river after river, partly from discipline, partly from training so thorough it overrode fear, but also from something else, a stubborn pride in the work itself. These men knew they were good. They knew they could do what others thought impossible. When a bridge went up in 3 hours instead of 10, when tanks rolled across ahead of schedule, when generals stood on the bank and stared in disbelief, the engineers felt it. Worth the terror. Worth the cold. Worth watching friends die beside them. Angle 2. Technological innovation. Speed by design, the CO. M2 Treadway Bridge was a marvel of modular engineering. Each section weighed 300 pounds, heavy enough to be sturdy, light enough for 4 men to carry. The sections locked together with steel pins that required no tools, just a hammer blow. Pneumatic floats attached to the underside via quick-release clamps. A single company could carry enough sections to span 200 meters, all transported on specialized trucks designed to reach the water's edge. Assembly followed a precise sequence drilled into muscle memory. First team positions anchor cables on both banks, measuring current speed and angle. Second team inflates pneumatic floats using hand pumps or motorized compressors, 60 seconds per float. Third team begins assembling the roadway on the near bank, connecting treadway sections in a line. Fourth team, working from boats, guides the growing bridge into the current, connecting floats as the span extends. Fifth team secures the far bank, anchoring the bridge against current and wind load. Under ideal conditions, a trained company could complete this in 4 hours. Under fire, in darkness with half the men wounded or dead, they completed it in 6. The Bailey Bridge offered different advantages: greater load capacity, more permanent construction. British engineers had designed it in 1940 with brilliance, a modular panel system where each section weighed 500 pounds, but could be assembled by hand without cranes or heavy machinery. Panels locked into a lattice structure strong enough to support tanks. Extensions could be added to increase span length. The same basic components built bridges from 20 meters to 200 meters. American engineer battalions adopted Bailey bridges enthusiastically, then modified them. They reduced assembly time by pre-positioning components, by color-coding panels to eliminate confusion and darkness, by assigning specific crews to specific tasks so no one wasted seconds deciding what to do next. They developed techniques for building Bailey bridges under enemy fire, constructing the span parallel to the river, then using winches to rotate it into position, minimizing exposure time. Innovation extended beyond bridges themselves. Engineer units developed specialized boats for river crossings, assault boats with outboard motors, large enough to carry a squad with equipment. They created portable ramps that allowed vehicles to drive directly onto pontoon spans, without bottlenecking at approach roads. They designed lighting systems that could illuminate work areas without creating targets for enemy artillery. Low-intensity lights shielded from the far bank, infrared markers visible only through specialized viewers. Every piece of equipment reflected lessons learned in blood. When pneumatic floats proved vulnerable to shrapnel, engineers added redundant compartments so a single puncture would not sink the section. When anchor cables parted under stress, metallurgists developed stronger alloys. When German artillery targeted the obvious approach roads, engineers built multiple access points, dispersing equipment to deny the enemy concentrated targets. Technology served speed, and speed saved lives. Angle 3, Training and Doctrine, the weapon of velocity, the 291st Engineer Combat Battalion arrived in France in November 1944 with a reputation. They had built 17 bridges in training exercises, each one faster than the last. Their record stood at 93 minutes for a functional M2 treadway span, capable of supporting medium tanks. Fort Belvoir instructors had called it impossible, then watched them do it twice more. The battalion's commanding officer, Lieutenant Colonel Harvey Fraser, drilled a single principle into his men. Every minute costs lives. Build fast or men die waiting. This was not metaphor. When infantry seized a bridgehead across a river, they were isolated, cut off from reinforcement, from resupply, from armored support. They held ground with what they carried. If engineers took 8 hours to build a bridge, infantry spent 8 hours under German counterattack with no heavy weapons, no tanks, no artillery support beyond what could fire from the western bank. Men died in those hours. Companies were overrun. Ground won at terrible cost was lost. If engineers built the bridge in 2 hours, infantry held with tank support by the 3rd hour. Casualties dropped. Bridgeheads expanded. The offensive continued. Speed was measured in lives saved. American engineer doctrine codified this into training at every level. Officers learned to plan bridge operations not from the completion time backward, but from the infantry assault forward. How soon could armor cross? How quickly could supply trucks move? What was the absolute minimum time acceptable? Then they trained to beat that minimum. NCOs drilled their squads until bridge assembly became choreographed. Each man knew his position in the sequence, knew the man working beside him, knew how to compensate if someone fell wounded. They practiced in rain, in darkness, with half the crew pulled randomly to simulate casualties. They practiced under live fire from overhead machine guns, learning to work while bullets cracked past. The psychological conditioning was deliberate. Men who panicked under fire were worthless on a bridge. Engineers needed to function through fear, to keep hands steady while explosions threw water 30 feet high, to maintain focus while friends died beside them. Training created this, not by eliminating fear but by making the work automatic. So muscle memory carried men through terror. By 1945, American engineer battalions crossing into Germany had achieved something remarkable. They had industrialized bridge construction, turned it from an engineering project into a production process. Crews rotated through positions to prevent fatigue. Reserve teams stood ready to replace casualties without breaking rhythm. Equipment staged in precise order so no one wasted seconds searching for components. The result was speed that seemed superhuman. German observers watching through binoculars from the far bank reported American bridges appearing as if by magic. Intelligence officers dismissed these reports as combat fatigue. Surely no force could work that quickly under fire. The reports persisted. Staff officers began to worry. They would soon discover the report's understated reality. Angle 4. German perspective, intelligence failure, and shockoburst. Heinrich Müller commanded the 89th Infantry Division on the western approaches to the Rhine in March 1945. He was 51 years old, a veteran of the Eastern Front, a professional soldier who had survived Stalingrad and the retreat through Ukraine. He understood defensive warfare. His division held 20 kilometers of riverbank, every meter pre-sighted, for artillery, every bridge demolished, every ford mined. The Rhine at this sector ran 400 meters wide with currents that reached 5 knots in the center channel. Müller's staff had calculated it would take American forces 3 to 5 days to establish a bridge capable of supporting armor. His artillery was ranged for maximum effect during those 3 days. On the morning of March 24, 1945, Müller received reports that American forces had reached the western bank during the night. Good. Expected. His orders were to allow them to begin bridge construction, then to destroy it with concentrated fire. The Americans would waste equipment, lose men, exhaust themselves. Then German counterattacks would crush the weakened bridgehead. By noon, his forward observers reported the Americans had completed a pontoon bridge. Müller assumed the report was an error. 12 hours was impossible. He called for confirmation. The observer insisted. A functional bridge, tanks already crossing. Müller drove forward to see for himself, arriving at an observation post 3 kilometers from the river. Through binoculars, he watched Sherman tanks rolling across a pontoon bridge, one every 90 seconds, a steady stream of armor flowing east. The bridge had not existed 10 hours earlier. Müller's first reaction was disbelief. His second was fury at his own artillery for failing to destroy it. His third, after reviewing the timeline with his staff, was something closer to awe. The Americans had built a bridge capable of supporting 50-ton vehicles in less time than it took to properly register artillery fire, coordinate airstrikes, and execute a sustained bombardment. They had worked through darkness under harassing fire and completed the span before German forces could mount an effective response. This violated every principle of military engineering Müller had learned. He was not alone in his shock. German officers across the Western Front filed similar reports through February and March 1945. American engineers building bridges overnight. Rivers crossed within hours of American forces arriving. Tank columns appearing on the eastern bank, impossibly fast. The reports accumulated at Wehrmacht headquarters, where staff officers struggled to explain them. Some theorized the Americans had prefabricated entire bridge sections, simply dropping them into place. Intelligence investigations found no evidence of this. Others suggested American air superiority allowed them to work unmolested. But reports confirmed engineers worked under fire, often heavy fire, and still completed bridges ahead of schedule. A few officers suggested American casualties must be catastrophic, that the speed came from throwing men at the problem without regard for losses. Prisoner interrogations proved otherwise. American engineer casualties were significant but not extraordinary. The men weren't dying at rates that explained the speed. They were simply working faster than German doctrine thought possible. General Major Otto Hitzfeld, commanding the L7 Corps defending the Remagen sector, later wrote in his diary, "We planned for the river to hold them for a week. It held them for a night. Our entire defensive strategy assumed time we were never given. The Americans cross rivers the way their tanks cross fields, as obstacles to be bypassed, not barriers to be overcome. The psychological impact on German defenders was immense. Soldiers who had fought in Russia, who had survived Normandy, who had retreated through France and Belgium, took morale from one certainty. Rivers were strong. Rivers stopped armies. Rivers gave exhausted troops time to rest, to regroup, to prepare the next defense. When that certainty evaporated, when American armor appeared across rivers within hours, the psychological foundation of German defensive strategy cracked. If rivers didn't stop them, what would? Angle 5. Tactical impact, armored momentum sustained Lieutenant General George S. Patton's Third Army reached the Rhine at Oppenheim on March 22, 1945. Intelligence reports indicated the Germans had demolished all bridges and established strong defensive positions on the eastern bank. Standard procedure called for extensive reconnaissance, artillery preparation, airstrikes to suppress enemy defenses, then a carefully planned assault crossing with engineer support to follow once a bridgehead was secured. Patton ordered the crossing to begin immediately. His engineers, elements of the 1303rd Engineer General Service Regiment, began assembling pontoon bridges at 2200 hours on March 22nd. They worked in near total darkness with minimal artillery support, under sporadic German fire from the far bank. Infantry crossed in assault boats, establishing a small bridgehead. Engineers continued construction, extending spans across the Black Water, fighting current and German mortar fire. At 800 hours on March 23rd, the first Sherman tank rolled across a completed pontoon bridge. 10 hours from start to finish. No air cover requested. No preliminary bombardment. The bridge simply appeared, and Third Army continued advancing as if the Rhine had never existed. Patton himself crossed the bridge later that day, deliberately, stopping midway to urinate into the river. A crude but effective piece of theater for the benefit of his troops and photographers. Behind the showmanship was a tactical revolution. Traditional river crossings broke offensive momentum. Attacking forces would reach a river, stop, stage equipment, prepare defenses while engineers worked, then resume the advance days later. This gave defenders time to reinforce, to reposition, to prepare the next defensive line. Time measured in days became weeks of operational pause. American engineer speed eliminated those pauses. When the 2nd Armored Division reached the Rhine River in February 1945, they expected a 3-day delay. Engineers had bridges functional in 18 hours. The armor crossed and pushed 30 kilometers deeper into Germany before German forces finished repositioning to defend the next river line. When the 4th Armored Division reached the Kyle River in early March, engineers built 3 separate bridges in a single night, 2 for tanks, 1 for supply trucks, and the division continued advancing without breaking stride. This had cascading effects on German defensive planning. Wehrmacht doctrine relied on trading space for time, fall back to a defensible line, force the Americans to stop and prepare, use that time to regroup and reinforce. But if American forces didn't stop, if rivers became mere hours-long pauses instead of days-long sieges, then German units found themselves constantly retreating, never fully recovering, always caught off balance. The operational tempo became unsustainable for German defenders. By late March 1945, American armored divisions were advancing 20 to 30 kilometers per day, speeds approaching those of the 1940 Blitzkrieg that had shattered France. But, unlike the Germans in 1940, American forces maintained this pace not just in open country, but across river-crossed terrain. Every river that should have stopped them for days stopped them for hours. The mathematics of collapse became inevitable. German forces needed time to fall back, establish new positions, resupply, integrate reinforcements. American engineer speed denied them that time. Units withdrew before defensive positions were complete. Supply lines stretched beyond sustainability. Command and control broke down as headquarters planned for defenses that were overrun before implementation. Engineers had weaponized time itself. Angle 6. Psychological warfare. The enemy's disintegration Feldwebel Klaus Dietrich surrendered to American forces on March 28, 1945, near Darmstadt. Interrogation officers found him surprisingly willing to talk. He was 26, a veteran of the Eastern Front, holder of the Iron Cross Second Class for action near Kharkov. He had survived 3 years of Soviet offensives, seen armies destroyed, watched Germany retreat 1,000 kilometers. He was not, by any measure, a man easily shaken. But when asked about American river crossings, his composure cracked. We watched them reach the river at dusk, he told his interrogators. We had blown the bridge. We had guns covering every meter of bank. We expected days of preparation, artillery duels, airstrikes. By morning, they had a bridge and tanks were crossing. Just crossing, as if the river wasn't there. We were told to counterattack, but men were asking what was the point. If they can build bridges overnight, if they cross rivers like they're nothing, where do we stop them? This was not an isolated reaction. Prisoner interrogations through March and April 1945 revealed a consistent pattern. German soldiers expressing shock, confusion, and hopelessness regarding American engineering capabilities. The speed violated their understanding of how war worked. It suggested resources so vast, competence so overwhelming, that resistance seemed futile. Some prisoners reported their officers had accused them of lying when they first reported American bridges completed overnight. The officers insisted it was impossible, that the men were exaggerating due to exhaustion or cowardice. When the same reports came from multiple units, from professional NCOs, from forward observers with no reason to lie, the realization settled in. The Americans were doing something fundamentally different. This was psychological warfare without propaganda, without intent. American engineers were simply executing their mission: build bridges, support the advance. They weren't trying to demoralize the enemy. But speed itself became a weapon, each bridge a demonstration of capability that eroded German will to resist. If the enemy could do in hours what should take days, what else were they capable of? What other assumptions were wrong? The psychological effect multiplied in units that faced multiple American crossings. Soldiers who had watched their own engineers struggle for days to bridge a river, who knew the complexity and time required, who understood the mathematics of engineering. These men watched American bridges appear in a fraction of that time and concluded they were facing an enemy with resources and skill so superior that victory was impossible. Morale collapsed before ammunition ran out. By April 1945, Wehrmacht units in some sectors surrendered not because they were encircled or out of supplies, but because continued resistance seemed pointless. If rivers couldn't stop the Americans, if defensive lines meant nothing, if every delay tactic failed, then why watch more men die for objectives that couldn't be held? The engineers had built more than bridges. They had built inevitability. March 7, 1945, 15:27 hours. Remagen, Germany. Sergeant Alexander Drabik of the 27th Armored Infantry Battalion became the first Allied soldier to cross the Rhine when he sprinted across the Ludendorff Bridge, a railway bridge the Germans had failed to demolish despite desperate attempts. Within hours, American forces poured across, establishing a bridgehead on the eastern bank. It was a stunning tactical victory, a gift of German incompetence and American audacity. But the bridge was dying. German engineers had damaged it in their demolition attempts. American tanks and trucks crossing at maximum capacity stressed the structure beyond design limits. Cracks appeared in the support towers. Steel cables frayed. Engineers inspected the bridge on March 9th and declared it unsafe but still functional. On March 10th, they restricted traffic to light vehicles. On March 11th, they ordered all personnel off the bridge while repair crews worked. At 1500 hours on March 17th, the Ludendorff Bridge collapsed into the Rhine. 28 American engineers died in the collapse, crushed under falling steel or drowned in the current. The bridgehead held more than 8,000 men and substantial armor, but they were now cut off from reinforcement and resupply. German forces, sensing opportunity, prepared counterattacks. Artillery intensified. The situation could have become catastrophic. An isolated force across Germany's greatest river with no way to sustain them. Lieutenant Colonel Clayton Rust, commanding officer of the 291st Engineer Combat Battalion, received orders at 15:20 hours, build a replacement bridge immediately under fire. At night, if necessary, His battalion had been in reserve, resting after 3 weeks of continuous operations. They had built 11 bridges since crossing into Germany in February. They were exhausted. They had lost 40 men to casualties and another 20 to illness and injury. The survivors were operating on caffeine, adrenaline, and willpower. Rust gave his company commanders 30 minutes to prepare. At 1600 hours, trucks loaded with M2 treadway components rolled toward the river. German artillery opened fire at 1615 hours. The first shells landed 200 meters short, throwing geysers of water and mud across the western bank. Forward observers on the eastern bank were calling fire missions to every available German battery within range. This was the target they had dreamed of. American engineers exposed on open water, forced to work slowly and methodically. Unable to hide or disperse, they expected to slaughter the bridge crews. Company A, 291st Engineers, reached the water at 1630 hours under sustained artillery fire. Captain James Gamble positioned his men along the bank, assigning tasks even as shrapnel hissed through the air. First platoon handled anchor cables. Second platoon inflated pneumatic floats. Third platoon began assembling treadway sections in a staging area, 50 meters from the water's edge. Men worked without speaking. Hands moving through sequences drilled into muscle memory. A shell landed 30 meters out in the river, the explosion sending a column of water 15 meters high. Corporal David Nunez, securing an anchor cable, disappeared beneath the spray. For 3 seconds, no one could see him. Then he emerged, soaked and shaking, still gripping the cable. He drove the anchor pin home and moved to the next position. By 1700 hours, the first treadway sections entered the water. Engineers and assault boats guided the sections into position, fighting current while artillery fire walked closer. The German gunners were ranging properly now, adjusting for wind and distance. Shells landed in a pattern, one short, one over, then a third that detonated directly above the water, airbursting shrapnel across the construction site. Private First Class Michael Torres took shrapnel through the shoulder. He fell into the water, pulled under by the weight of his equipment. Sergeant James Keller dove after him, dragging him to the bank where medics waited. Torres was evacuated. Keller returned to his position, blood streaming from a cut above his eye, and continued working. The bridge grew. Section by section, float by float, the span extended from the western bank toward the east. Engineers worked in teams of 4, each man knowing his position, his task, his timing. When one man fell wounded, another moved into position without orders. When equipment failed, crews improvised, using cable intended for anchors to replace damaged securing lines, using engineer tape to patch torn pneumatic floats, using sheer determination to compensate for missing components. By 1800 hours, the bridge stretched 100 meters across the Rhine. German artillery shifted to targeting the far end of the construction, trying to prevent engineers from securing the eastern bank. Shells landed in sequence, a rolling barrage that threw mud and fragments across the approach road. Engineers waiting on the eastern side pressed themselves into shallow fighting holes dug by infantry, waiting for the barrage to lift. At 1815 hours, the shelling paused, German guns repositioning or reloading. Engineers on the eastern bank sprinted to the water's edge. They had less than 2 minutes before fire resumed. They grabbed the anchor cables being floated across and drove the pins deep into the muddy bank. 1 pin, 2, 3. The bridge section pulled taut as current and wind load transferred to the anchors. Artillery resumed at 1817 hours. Captain Gamble, coordinating from the western bank, watched a shell land directly on the far shore where his men had been working seconds before. Earth and smoke obscured the area. He couldn't tell if anyone had been hit. Radio communication was sporadic. Electrical interference from the explosions disrupted signals. He waited, counting seconds, until a green flare arced up from the far bank, the signal for anchors secure. By 1900 hours, the bridge reached 200 meters, 3/4 complete. But darkness was falling, and German fire intensified as if the enemy understood time was running out. Shells landed in patterns now, coordinated fire from multiple batteries. Machine guns on the far bank opened up, tracer rounds arcing across the water in brilliant red lines. The engineers had no choice but to continue. Stopping now meant failure, meant the bridge had remained isolated, meant men died for nothing. They kept building. At 1945 hours, Sergeant Thomas Riley was killed instantly by a direct shell hit. He had been securing the final treadway section when the round landed 3 meters away. The explosion threw his body into the river. His crew paused for 3 seconds, not from fear, not from grief, but from pure mechanical necessity to process what had happened. Then they returned to work, completing the section Riley had died finishing. The bridge reached the eastern bank at 2018 hours, 5 hours and 18 minutes from start to finish. A pontoon bridge spanning 400 meters of the Rhine River, built under sustained artillery fire, capable of supporting medium tanks. Engineers on both banks secured the final anchor cables, bolted the last treadway sections into place, positioned guide ropes for vehicles. At 20:30 hours, a jeep crossed as a test. It wobbled slightly in the current but held steady. At 20:45 hours, the first Sherman tank rolled onto the western end of the bridge. The tank commander hesitated at the bridge entrance. He could see the Rhine current pushing against the pneumatic floats. See the bridge flexing slightly under wind load. See engineers standing at intervals along the span with flashlights marking the safe path. The bridge looked fragile, too fragile for 50 tons of armor and steel. Behind him, 12 more tanks waited in column, engines idling, crews watching. Captain Gamble waved him forward. The Sherman rolled onto the first treadway section. The bridge dipped 6 inches under the weight, then stabilized. The tank continued, moving at walking speed, treads gripping the steel surface. Engineers along the span watched the pontoons, checking for signs of stress or failure. The current pushed harder as the tank reached midstream, the entire bridge shifting slightly downstream before the anchor cables caught and held. At 20:52 hours, the Sherman reached the eastern bank. The second tank started across immediately. Then the third. By 2100 hours, 7 tanks had crossed without incident. By 21:30 hours, armored vehicles moved across the bridge in steady flow, 1 every 3 minutes, coordinated by engineers with radios and flashlights. The bridgehead was no longer isolated. Armor poured in, followed by supply trucks, artillery tractors, engineer vehicles with additional bridging equipment. German observers watched through the darkness and realized their counterattack had just become impossible. At Wehrmacht headquarters, 15 kilometers east, Oberst Müller received the report at 2200 hours. An American bridge, functional, supporting armor. Built in 5 hours. He stared at the message, read it twice, then called his intelligence officer. How many bridges do they have across the Rhine now? 3 functional, sir. The pontoon bridge at Remagen. A Bailey bridge at Erpel completed this afternoon, and reports indicate another pontoon bridge under construction at Linz, expected completion within hours. 3 bridges. Within 24 hours of the Ludendorff collapse, Müller had planned his counterattack, assuming the Americans would need 3 to 5 days to restore crossing capability. His artillery had pre-planned fire missions based on that timeline. His infantry were positioned for an assault on an isolated bridgehead, not against reinforced positions with armor support. The counterattack was canceled at 22:30 hours. There was nothing to counterattack against. The bridgehead was no longer vulnerable. American forces on the eastern bank numbered over 20,000 by midnight, with armor and artillery sufficient to crush any assault German forces could mount. The Rhine, Germany's greatest natural defense, had been breached and bridged so quickly that defensive strategy collapsed before it could be executed. General George S. Patton learned of the Remagen bridge construction while planning his own Rhine crossing 100 kilometers south. He immediately accelerated his timeline. If engineers could build a bridge at Remagen in 5 hours under fire, his Third Army engineers could do the same at Oppenheim with proper preparation. He ordered assault boats forward, artillery positioned for maximum suppression fire, and engineer battalions brought to readiness. On the night of March 22, 23, Patton's forces crossed the Rhine at Oppenheim with minimal opposition. Engineers from Mauperdu, the 1303rd Regiment, began bridge construction at 2200 hours. They worked with practiced efficiency, laying out equipment in staging areas, positioning boats for ferry operations, coordinating with infantry securing the far bank. German artillery fire was sporadic. Wehrmacht forces in this sector were depleted, ammunition scarce, command structure fractured by weeks of retreat. The engineers barely slowed. By Ordo 200 hours on March 23rd, they had completed a light pontoon bridge for infantry and vehicles. By Oro 600 hours, they had finished a heavy pontoon bridge capable of supporting tanks. By Oro 800 hours, they began construction on a Bailey bridge for sustained heavy traffic. Patton's crossing achieved complete surprise not through deception but through speed. German commanders assumed they had days to prepare defenses. They had hours. Third Army tanks rolled across the Rhine before German reinforcements arrived. Further north at Wesel, British and Canadian forces launched Operation Plunder on March 23rd. A massive, meticulously planned Rhine crossing supported by airborne drops and the largest artillery barrage since D-Day. Engineers from multiple nations worked to establish bridges under this umbrella of overwhelming firepower. American engineer units attached to British forces demonstrated the techniques developed over months of combat. Sergeant William Foster of the 1159th Engineer Combat Group worked with British engineers building a Bailey Bridge at Wesel. The British crews followed standard procedure: careful measurement, precise alignment, methodical assembly. Foster's American crew worked alongside them using modified techniques: pre-positioned components, parallelized tasks, constant motion. The British completed their section in 8 hours. The American section was functional in 5. A British officer watching the American crew's work remarked to Foster, "You chaps build bridges like you're assembling bicycles." "Remarkable," Foster replied. "Sir, we build them like our lives depend on finishing fast, because they do." By March 25th, Allied forces had established 14 major bridges across the Rhine between Arnhem and Mannheim. The river that was supposed to delay the Allied advance for weeks had been crossed and bridged in days. German defensive strategy, predicated on using rivers as force multipliers, had been rendered obsolete. Captured German officers, interrogated in late March, expressed variations of the same shock. Major Friedrich Weber, former chief engineer, for the 89th Infantry Division, "We calculated they would need a week minimum to establish reliable crossings. They built bridges faster than we could destroy them. Our own engineers require 2 days under ideal conditions for similar bridges. The Americans did it in half a day under artillery fire. This is not skill. This is industrial capacity translated to the battlefield." He was wrong about one thing. It was skill. Skill trained into 600 men per battalion, rehearsed until bridge construction became instinct, refined through dozens of river crossings under combat conditions. But it was also capacity, American. Logistics that kept equipment flowing forward. American industry that produced thousands of bridge sections. American doctrine that treated speed as a weapon. By April 1, 1945, American armored divisions were operating 50 to 100 kilometers beyond the Rhine. The rapid bridging had shattered German defensive planning. Units that should have had time to establish positions in depth found themselves overrun before entrenchment was complete. Supply lines that should have been secure were cut by fast-moving American columns. Command posts that should have been safe were captured before headquarters staff could evacuate. The Rhine, Germany's greatest defensive barrier, had become just another river crossed in a night. General Feldmarschall Albert Kesselring, commander of German forces in the West, wrote in his diary on April 3rd, "The speed of American engineering operations has made static defense impossible. We cannot hold river lines if bridges appear overnight. We cannot counterattack bridgeheads that are reinforced within hours. Traditional defensive doctrine assumes time we are no longer given. The Americans have made time itself into their weapon." The engineers had achieved something beyond tactical success. They had broken the fundamental logic of defensive warfare in river-cross terrain. They had proven that with sufficient training, equipment, and determination, barriers became delays, delays became inconveniences, and inconveniences disappeared entirely. They had turned rivers into roads, and in doing so, they had opened the path to Berlin. The Rhine crossings of March 1945 cost the 291st Engineer Combat Battalion 43 men killed and 97 wounded. They built 7 bridges in 18 days. Every bridge was completed ahead of the timeline provided by divisional planning. Every bridge supported the crossing of multiple armored divisions. Every bridge remained functional until permanent Bailey Bridge replacements could be constructed. Captain James Gamble received the Silver Star for his actions at Remagen. Sergeant Thomas Riley received the Bronze Star posthumously. The battalion received a Presidential Unit citation. The numbers tell part of the story. Between March 7 and April 1, 1945, American engineer units built 53 major bridges across the Rhine and its tributaries. An additional 112 pontoon bridges crossed secondary rivers throughout western Germany. Engineer casualties during this period totaled 1,247 killed and 3,891 wounded, roughly equivalent to an infantry division's losses during a major offensive. But those casualties enabled the crossing of 6 full armies comprising over 1 million men. The strategic impact was immediate and catastrophic for German forces. Wehrmacht planning documents captured in April revealed the extent of miscalculation. German staff officers had projected the Rhine would delay Allied forces for 3 to 6 weeks, allowing time to transfer divisions from other fronts, to establish defensive positions in depth, to organize the defense of Germany's industrial heartland. They received days instead of weeks. By April 10th, American forces had advanced 150 kilometers beyond the Rhine. The Ruhr industrial region, Germany's economic core, was encircled by April 18th. Model's Army Group B, trapped in the pocket, surrendered on April 21st with 325,000 men. This was larger than the Stalingrad encirclement, achieved in a fraction of the time, made possible because rivers had not stopped the Allied advance. German commanders in western Germany surrendered in increasing numbers through April. Many cited the futility of continued resistance. Oberst Heinrich Müller, the same officer who had watched American bridges appear overnight at Remagen, surrendered his remaining forces on April 15th without a fight. During interrogation, he was asked why he had not attempted to hold his positions. His response was recorded in Allied intelligence files. Hold with what? Against what? They cross rivers in hours. They bring tanks across water as if it were solid ground. Every defensive position we prepare is bypassed before it can be properly manned. Continued resistance would achieve nothing except the death of my men. This was the psychological aftermath, the collapse of will before the collapse of capability. German forces in the West still possessed weapons, ammunition, and manpower in mid-April 1945. What they lacked was belief that these resources could achieve anything meaningful. American engineering speed had demonstrated such overwhelming capability that resistance seemed pointless. If the enemy could bridge the Rhine overnight, what defensive position could possibly hold them? The material aftermath was equally significant. American engineer units began transitioning from assault bridging to infrastructure restoration. The same men who had built pontoon bridges under fire now constructed permanent crossings, repaired railways, cleared rubble from roads, restored water systems to German cities. The 291st Engineer Combat Battalion, after 18 days of continuous combat operations, spent May and June rebuilding civilian infrastructure in occupied Germany. The irony was not lost on the engineers. They had destroyed bridges to deny them to the enemy, then rebuilt them to support occupation. They had fought to cross rivers, then worked to make those crossings safe for civilian use. War and reconstruction blurred together in those final weeks, the same men performing both roles with equal competence. Allied casualty statistics revealed a striking pattern. Infantry divisions that had engineer support for rapid river crossings suffered 20 to 30% fewer casualties than divisions that faced prolonged river assault operations. The speed saved lives, both by maintaining offensive momentum and by reducing the time soldiers spent exposed during crossing operations. Armored divisions with dedicated engineer battalions advanced 30% faster than units that had to wait for corps-level engineer support. Speed had proven itself not just as a tactical advantage, but as a casualty reduction measure. Post-operation, reports filed by engineer battalions in April 1945 documented lessons learned. Equipment modifications were recommended: stronger anchor cables, more efficient float inflation systems, improved lighting for night operations. Training recommendations emphasized night construction and operation under simulated artillery fire. Doctrine updates codified the techniques developed in combat: parallelized construction, pre-positioned components, dedicated reconnaissance teams. These reports would shape American military engineering for decades, but the immediate aftermath was simpler, more personal. Engineers who had worked through exhaustion, who had watched friends die in the water, who had built bridges while shells landed around them, these men rested. They slept for days in some cases, the adrenaline finally depleted, the body demanding payment for weeks of impossible effort. Private First Class James Delmont, who had written home in February about carrying cables instead of rifles, wrote again in late April. "We built 19 bridges since we crossed into Germany. I don't remember most of them. They blur together. Cold. Water, shells falling, hands so numb I couldn't feel the tools. But we built them. Everyone. And we're alive. Most of us. That's the aftermath. We're still here, and Germany isn't." The engineers had won their war. Now they had to figure out what came next. The German military conducted its own accounting in the months after surrender. General Major Otto Hitzfeld, captured at Remagen and held at a POW camp in France, spent his captivity writing a detailed analysis of the Rhine defense's failure. His report, later recovered by Allied intelligence officers, concluded, "American engineering capability was the decisive factor. We planned for a defensive operation measured in weeks. We received hours. Every calculation, every tactical decision, every strategic disposition was predicated on time we were never given. Our defeat was not inevitable when American forces reached the Rhine. It became inevitable when they crossed it within days." Other German officers reached similar conclusions. Post-war interviews conducted by the U.S. Army Historical Division revealed a consistent theme. German commanders had fundamentally underestimated American engineering speed. This was not ignorance. German intelligence had access to captured American field manuals, had interrogated engineer prisoners, had observed American bridge construction at earlier river crossings. But the data seemed impossible, so it was discounted or explained away as exaggeration. Reality had shattered assumption. Oberst Werner Osterkamp, former Chief of Staff for L-7 Corps, stated in a 1946 interview, "We knew American engineers were well equipped. We knew they had excellent bridging equipment. What we failed to understand was that they had industrialized the construction process itself. They built bridges the way their factories built tanks, with assembly line efficiency, standardized procedures, specialized crews. We treated bridge construction as an engineering problem. They treated it as a production problem. The distinction was profound." German military doctrine, like most traditional military thinking, viewed bridge construction as a technical challenge requiring skilled engineers working methodically. American doctrine had reconceptualized it as a time-critical operation, where speed mattered more than perfection. A bridge that was adequate but built in 3 hours was more valuable than a perfect bridge that took 10 hours, because the 3-hour bridge enabled operational tempo that the 10-hour bridge destroyed. This philosophical difference had decided the campaign. By May 1945, American engineer units had built over 300 major bridges across Germany and France. They had cleared thousands of kilometers of roads, repaired hundreds of rail lines, restored water systems to dozens of cities. The same organizational capacity that had enabled rapid combat bridging now accelerated post-war reconstruction. German civilians in occupied zones noticed infrastructure that had been destroyed in fighting was being restored faster than German authorities had managed even during peacetime. Roads cratered by bombs were repaired in days. Railway bridges, demolished by retreating Wehrmacht forces, were rebuilt in weeks. American engineer units applied combat-developed speed techniques to reconstruction. Prefabricated components, specialized crews, parallelized operations. The Marshall Plan's success, years later, would rest partially on these foundations. American organizational capacity for large-scale infrastructure projects, proven effective under the worst possible conditions. The legacy extended beyond infrastructure. American military engineering doctrine became the global standard. NATO forces adopted American bridging systems and training methods. The Soviet Union, studying captured German reports of American operations, modified its own engineer training to emphasize speed. By the 1950s, military engineers worldwide were being taught techniques developed by American combat engineers in 1944-45. The M2 Treadway Bridge remained in U.S. military service until the 1990s, testament to its effective design. The Bailey Bridge is still in use worldwide, both military and civilian applications, 75 years after its combat debut. Modern military bridging systems are descendants of these World War II innovations, refined and improved, but based on the same fundamental principles: modularity, speed, simplicity. Individual engineers returned home to varied fates. Captain James Gamble left the Army in 1946, earned a civil engineering degree on the GI Bill, and spent 30 years building bridges for state highway departments. He never spoke publicly about his war service until 1985, when a local newspaper interviewed him for the 40th anniversary of VE Day. He told the reporter, "We did what we were trained to do. The remarkable thing wasn't that we built bridges fast. It was that the Army had figured out how to train us to do it." That's the real story. Not individual heroism, but institutional competence. Sergeant William Foster remained in the Army, retiring as a lieutenant colonel in 1967. He taught military engineering at West Point for 8 years, passing on techniques learned in combat to a new generation of officers. His students included engineers who would serve in Vietnam, where river crossings remained challenging despite decades of technological advancement. Foster's lectures emphasized that equipment mattered less than training, that speed came from rehearsal, that bridges were built by men before they were built by machines. Private First Class James Delmont returned to Ohio, worked in a steel mill, raised 4 children. He never joined veterans organizations, never attended reunions. His family found his medals in a drawer after his death in 1998: Bronze Star, Purple Heart, Presidential Unit Citation. Also in the drawer, a photograph of a pontoon bridge across dark water, location and date unknown, taken by someone whose name Delmont had never recorded. The 291st Engineer Combat Battalion was deactivated in 1946. Its colors were cased and stored at Fort Belvoir. The unit was reactivated for Korea, served with distinction, deactivated again, reactivated for Vietnam, deactivated, reactivated. The continuous lineage maintained through decades. The unit's World War II service forming the core of its identity. Statistical analysis conducted by the U.S. Army Corps of Engineers in 1948 quantified the impact of rapid bridging on the European campaign. Engineer-supported divisions advanced an average of 12 kilometers per day during the final months of the war. Divisions without dedicated engineer support averaged 7 kilometers per day. The difference, 5 kilometers daily, accumulated across weeks into strategic advantage. Mathematical modeling suggested that without rapid bridging capabilities, the war in Europe would have extended into summer 1945, possibly longer. Thousands of lives saved through speed. The analysis estimated that rapid Rhine crossings reduced Allied casualties by 15 to 20,000. By maintaining momentum, by preventing German forces from establishing static defensive lines, by keeping the enemy off balance, American engineers had achieved casualty reduction equivalent to winning a major battle, except they had done it through construction rather than destruction. This became a key lesson incorporated into post-war military planning. Cold War. NATO strategy for defending Western Europe against Soviet attack relied heavily on engineer units capable of rapid bridge demolition and reconstruction. The assumption was that Soviet forces, like German forces in 1945, would be slowed by major rivers. Western engineers would demolish bridges during retreat, then rebuild them during counteroffensive. Speed of bridging became a critical metric in war games and exercises. The irony was that Soviet military planners, having studied the same German reports, had reached the same conclusions about engineering speed. Cold War rivalry thus included competition in bridge construction times. Which side could build faster? Which doctrine was more efficient? Which equipment was superior? The contest never turned hot, but exercises on both sides of the Iron Curtain featured timed bridge-building competitions. American engineers consistently performed well. By the 1980s, U.S. Army engineers could construct a medium girder bridge, successor to the Bailey Bridge, in under 4 hours. Modern ribbon bridges could be launched across rivers in 90 minutes. The times kept dropping, the technology improving, but the fundamental principle remained unchanged. Speed saves lives, momentum wins wars. Bridges built quickly are worth more than bridges built perfectly. All of it traced back to those desperate nights in 1945, to engineers working in darkness while shells fell around them, to men who built spans across German rivers faster than anyone thought possible. The aftermath was victory. But more than that, it was validation of a doctrine, proof of a principle, demonstration that human determination combined with proper training and adequate equipment could achieve what seemed impossible. The engineers had not just crossed rivers. They had redefined what was possible in modern warfare. War is remembered for its battles, its generals, its moments of heroic violence. The history books record tank clashes and infantry assaults, airborne drops and amphibious landings. They speak of Patton's dash across France, of Eisenhower's strategic decisions, of soldiers storming beaches under machine gun fire. These stories matter. They deserve remembrance. But wars are not won by destruction alone. For every bridge destroyed to slow an enemy, another must be built to continue the advance. For every road cratered by bombs, another must be cleared for supply trucks. For every river that becomes a barrier, engineers must make it a crossing. War is as much about building as breaking, about construction as much as combat. The men who built pontoon bridges across German rivers in 1945 were not celebrated heroes. They received their medals, filed their reports, and returned home to ordinary lives. No films dramatized their work. No monuments bore their names. History moved on, and they moved with it, carrying memories of cold water and falling shells that they rarely shared. Yet their achievement echoes through decades. They proved that speed itself could be a weapon, that time saved was lives preserved, that momentum maintained was victory accelerated. They demonstrated that proper training could make the impossible routine. That doctrine, carefully developed and rigorously practiced, could overcome what seemed like insurmountable obstacles. They showed that wars are won not just by brave men with rifles, but by determined men with tools. The German generals who watched American bridges appear overnight were not wrong to be stunned. They were witnessing something genuinely revolutionary. Not new technology, not overwhelming numbers, but the application of industrial thinking to military operations. The Americans had taken a complex engineering task and made it a production process, had turned bridge construction from an art into a science, from a project into a procedure. This was America's particular genius in the Second World War, not courage alone, not resources alone, but the combination of both with systematic efficiency. Other nations had brave soldiers. Other nations had industrial capacity. But America organized its resources and trained its men with a focus on speed and efficiency that other militaries struggled to match. The engineers building bridges in darkness while artillery fell embodied this. They were not superhuman. They were ordinary men made extraordinary through training, through doctrine, through a military system that had thought carefully about how to turn capability into reality. Their legacy lives in every modern military bridge, in every doctrine that emphasizes speed, in every training program that pushes men to work faster than they thought possible. It lives in the understanding that in war, as in so much of life, time matters, that delays cost, that momentum once lost is hard to regain. But perhaps the deepest legacy is simpler. Wars require not just warriors but builders, not just those who can destroy, but those who can create under the worst possible conditions. The engineers who crossed German rivers in 1945 remind us that victory requires both. The soldier who takes ground, and the engineer who makes that ground usable, the tank that breaks through and the bridge that allows it to continue. They built in darkness under fire, through exhaustion and fear. They built when it seemed impossible, when friends died beside them, when every rational calculation suggested they should stop. They built because stopping meant failure, meant men died waiting, meant victory delayed, and so they kept building. River after river, bridge after bridge, until the war was won, not through destruction but through creation, not through tearing down, but through building up. One span at a time, faster than anyone thought possible, they built the road to victory. That is what the German generals saw when they watched American bridges appear overnight. Not just engineering competence, not just industrial might, but something more fundamental, the determination to build even when the world was burning, to create even in the midst of destruction, to move forward no matter what stood in the way. They built bridges, and in doing so they built victory itself.